Welcome! In this session, we'll be tackling LeetCode problem number 770, Basic Calculator 4. This is a fascinating problem that combines parsing, algebraic manipulation, and efficient computation. We'll explore the problem, break it down step by step, and review an approach to solve it. Let's dive in. In this problem, we are tasked with simplifying a mathematical expression that can include integers, variables, and arithmetic operations like addition, subtraction, multiplication, and parentheses. Variables are represented as lowercase English letters, and the result must be formatted as a list of terms. Each term follows a specific format. If the coefficient of a term is 1, we omit it, so a*b would be used instead of 1*a*b. However, if the coefficient is -1, we include just the negative sign, like a*b instead of -1*a*b. Additionally, the variables in each term must appear in alphabetical order, so a*b is expected instead of b*. The problem also introduces the concept of known variables. We are provided with a list of variable names and their corresponding values, which can be used to evaluate parts of the expression. Any variables not included in the known values should remain as they are in the output. The output of this problem is a list of terms, formatted as described earlier and sorted lexicographically. Let's look at the first example to understand this better. The input expression is e plus 8 a plus 5, and we are given that the variable e has a known value of 1. Using this information, we can substitute 1 for e in the expression, which simplifies to 1 plus 8 a plus 5. From here, we proceed to simplify the constants and evaluate the expression further, keeping variables like a untouched if they are not part of the known values. After substituting the known value for e, we simplify the constants in the expression. Combining 1, 8, and 5 gives us 14, so the simplified expression becomes -1** and 14. These terms are then sorted lexicographically, resulting in the output list, -1*, 14. Now, consider another example where the input is abc plus bac*, 4, and no variable replacements are provided. Since there are no known variable values, we work directly with the terms in the expression. Here, *b*c and *a*b*c are like terms, so they can be combined into a single term 5*a*b*c. The final output for this example is the list, 5*a*b*c. In the third example, the input expression is simply 7 to 7, and again no variable replacements are provided. Simplifying this expression results in a constant value of 0. Since the final result is 0, the output is an empty list. This example demonstrates how the problem handles cases where there are no remaining terms to include in the output. The constraints ensure that all inputs are manageable in size, such as limiting the length of the expression to 1,000 characters and the number of known variables to 100. These constraints help guide how the solution should be implemented efficiently. The problem also defines that all intermediate calculations in the final result will not exceed 2 to the power of 31 in absolute value, ensuring we don't need to handle excessively large numbers. There are several edge cases to consider. For instance, if the expression contains only integers and no variables, the result should simplify to a single constant term. If no known variable values are provided, we must simplify the expression while leaving the variables untouched. Additionally, if the final result of the expression is 0, the output should be an empty list. Nested parentheses require careful handling to ensure that operator precedence is maintained, and large expressions with many terms must be correctly simplified and sorted lexicographically. By addressing these edge cases and adhering to the constraints, we can build a robust solution to this problem. To start, the brute force approach aims to solve the problem by directly evaluating the expression through recursive parsing. Think of the expression as a series of nested operations. Each sub-expression is resolved step by step, handling variables as placeholders or substituting their values. Multiplication and distribution are managed explicitly. The key steps include parsing the expression to identify terms, variables, and operations, then using recursion to handle nested parentheses. Once we expand the expression, we simplify it by distributing multiplication over addition or subtraction and combining like terms, often with the help of a data structure to organize the results. While this approach is straightforward and closely mirrors the problem description, it has significant trade-offs. It's computationally expensive, as the time complexity can grow exponentially with the depth of nested parentheses and the number of terms. This makes it impractical for large or complex inputs, despite being easy to implement for smaller cases. Now, the optimized approach uses a polynomial representation to simplify the problem. Instead of repeatedly parsing the expression as a string, we represent it as a collection of terms, essentially treating it like a polynomial. Each term is expressed as a tuple, where the first element is the coefficient and the second is a sorted list of variables. By organizing the expression this way, we can directly manipulate and simplify it without redundant parsing. Key steps involve tokenizing the input expression, representing terms as tuples, and leveraging dictionaries to combine like terms efficiently. For example, each unique combination of variables acts as a dictionary key, and the coefficients are accumulated accordingly. Using this structured format, we implement operations like addition, subtraction, and multiplication directly on the polynomial. Additionally, terms are ordered lexicographically to ensure the final output meets the required format. This approach is more scalable and efficient, with a complexity that grows polynomially with the input size. However, implementing these polynomial operations requires attention to detail, and the code becomes slightly more complex compared to the brute force solution. An alternative method involves leveraging symbolic computation libraries such as SymPy in Python. These libraries are specifically designed for symbolic algebra, making them a powerful tool for parsing, simplifying, and evaluating mathematical expressions. The process begins by parsing the expression into a symbolic form using the library. Then, built-in functions handle tasks like distribution, simplification, and substitution, significantly reducing the amount of manual implementation required. Once the simplification is complete, the result is converted back into the format specified by the problem. This approach has the advantage of requiring minimal coding effort, as you're relying on well-tested, robust library implementations. However, there are trade-offs. Relying on external libraries introduces dependencies and doesn't always align perfectly with the constraints of the problem. Additionally, the efficiency of this method depends heavily on the library's internal implementation, which may not always be optimal for every use case. The chosen strategy for this problem is the optimized approach using polynomial representation. This approach strikes a balance between clarity and efficiency. By structuring the problem as polynomial algebra, we avoid redundant operations and can systematically handle distribution, simplification, and the combination of terms. While symbolic computation libraries offer convenience, they introduce external dependencies and may not align precisely with the problem's constraints. On the other hand, the brute force approach, though intuitive, is computationally inefficient and unsuitable for complex inputs. A key realization here is that representing the expression as a dictionary of terms allows us to combine like terms efficiently. Furthermore, operations like distribution and substitution are intuitive to implement when mapped to dictionary manipulations. By sorting terms lexicographically, we ensure the output format adheres to the problem requirements without adding extra overhead. While this approach requires careful implementation of polynomial operations, the efficiency gains far outweigh the added complexity in coding. Finally, the time complexity of this approach is polynomial in the size of the input expression. This is because we operate directly on a structured representation of the data, rather than repeatedly parsing the string. This optimal balance between efficiency, clarity, and adherence to the problem's requirements makes the polynomial representation the most suitable strategy for solving this problem. It ensures that we can handle large and complex expressions effectively while maintaining a systematic and structured implementation. To begin solving this problem, the first thing we need to do is parse the input expression. This means breaking down the input string into its fundamental components, such as numbers, variables, and operators. To achieve this, we traverse the string character by character, identifying and separating these components. A stack is particularly useful for managing nested parentheses or maintaining operator precedence, as it allows us to handle the hierarchical structure of the expression. By separating operands and operators into distinct tokens, we create a clear representation of the expression. Parsing is crucial because it establishes the structure of the input, which is essential for evaluating it in a logical, step-by-step manner. Once parsing is complete, the next step is to handle variables or substitution. If the expression contains variables, we need to either replace them with their corresponding values assuming they are known or treat them as symbolic placeholders. A dictionary is ideal for this purpose, as it maps variable names to their values. During the parsing process, we can check this dictionary to substitute values or retain the variable as a placeholder if no value is provided. This substitution step simplifies the expression when possible, while also preserving any unknown variables for further evaluation down the line. After parsing and handling variables, the next step is to evaluate the expression itself. This involves recursively computing its value, starting with the innermost parentheses and working outward. The stack plays a central role here as well. It helps us manage operators and operands while respecting the precedence of operations. When we encounter a closing parenthesis, for example, we can use the stack to isolate and evaluate the sub-expression it encloses. By applying operators in the correct order, we ensure that the computation adheres to mathematical rules. This recursive breakdown not only ensures accuracy but also enables us to apply the same logic to nested components of the expression. Beyond evaluation, we also need to handle multiplication and distribution, especially when dealing with symbolic terms. For instance, if the expression includes something like 2 multiplied by a variable, we keep it in distributive form. Additionally, we combine like terms whenever possible, ensuring the expression remains as simplified as it can be. This process of distributing and simplifying lays the groundwork for further analysis or computation, making the expression easier to work with in subsequent steps. Once we've evaluated and handled the components of the expression, it's time to combine the results into a final output. If the expression contains only numeric values, we compute the final value directly. However, if it includes symbolic terms, we return the simplified symbolic representation as the result. This step ensures that all parts of the expression are aggregated into a cohesive answer, whether that answer is a number or a symbolic form. Several key insights come into play here. First, recursive parsing aligns perfectly with the hierarchical nature of nested expressions, making it an effective approach. Second, using a stack is essential for correctly managing parentheses and operator precedence, ensuring that the structure of the expression is handled properly. Finally, treating unknown variables as symbolic placeholders adds flexibility, enabling us to handle symbolic computation without losing the integrity of the original expression. To support these operations, we rely on specific data structures. A stack is used for managing nested parentheses and operator precedence, a dictionary maps variable names to their respective values for substitution, and a list stores tokens for easy traversal and manipulation. Together, these tools allow us to parse, evaluate, and simplify the expression efficiently. When analyzing the complexity of our approach, we find that the time complexity is n squared, in the worst case. This is primarily due to the recursive parsing and the handling of deeply nested structures, as each level of nesting adds additional processing overhead. On the other hand, the space complexity is n. This is because we use a stack to manage nested parentheses and operator precedence, as well as additional space for token storage. These complexities highlight the trade-offs of our recursive and stack-based approach, which, while effective, can become resource-intensive for highly nested or large expressions. Despite this, the algorithm is well suited for handling the problem's requirements, providing both correctness and flexibility in evaluating and simplifying mathematical expressions. Here, we begin by importing the necessary modules, defaultdict from collections and ru_cache from functools, to help manage default values in dictionaries and optimize recursive functions. Next, we define the solution class and the basic calculator IV method. This method takes 3 arguments: the mathematical expression as a string, a list of variables, and their corresponding integer values. Inside, the tokenize function is defined to break the input expression into a list of tokens. It iterates through the expression character by character, identifying operators like plus, dash, and asterisk, as well as multi-character tokens such as variable names or numbers. These tokens are appended to a list, which is returned at the end. Additionally, the combine_terms function is written to simplify polynomials by grouping like terms. It uses a defaultdict to aggregate coefficients of terms with the same variables, ensuring that only non-zero terms are included in the final output. The evaluate function is introduced here to process the tokenized expression and compute its result. Inside, we have a nested parse function, which uses two stacks, one for operands and one for operators. The apply_operator function is defined to handle basic arithmetic operations. Depending on the operator, it pops two operands from the stack, applies the operation, and pushes the result back onto the stack. As the parse function iterates through the tokens, it distinguishes between numbers, variables, and operators. Numbers and variables are wrapped into polynomial objects and pushed to the operand stack, while parentheses are handled by pushing or popping operators accordingly. When encountering an operator like plus, dash, or asterisk, the function considers operator precedence to decide whether to immediately evaluate or defer the operation. The evaluate function continues by managing operator precedence using a dictionary, where multiplication has higher precedence than addition or subtraction. After iterating through all tokens, any remaining operations in the operator stack are applied in sequence. The result of the parse function is the final computed polynomial. Next, we define a polynomial class to represent and manipulate polynomial expressions. The constructor initializes the polynomial's terms using a default dict. It can accept a dictionary to define specific terms and coefficients, or a constant value. The polynomial class supports addition, subtraction, and multiplication of polynomials. The __add___ method merges terms from both polynomials, combining coefficients of matching terms, while ensuring no terms with zero coefficients are retained in the result. The __sub___ method is similar to addition but subtracts coefficients of terms from the other polynomial. For multiplication, the __mul___ method computes the product of two polynomials by iterating through all term pairs. It combines the variables of each pair, sorts them, and computes the new coefficient as the product of the original coefficients. The resulting terms are stored in a new polynomial. Additionally, the substitute method allows replacing variables in the polynomial with specific values provided in a mapping. This is done by iterating through each term, and for each variable in the term, its coefficient is updated based on the mapping. If a variable is not in the mapping, it remains unchanged. The result is a simplified polynomial with constants replacing substituted variables and is returned for further processing. Finally, the to_list method is defined to convert the polynomial into a list of human-readable terms. Terms are sorted by their length and lexicographical order, and each term is formatted with its coefficient and variables joined by asterisk. Returning to the basic calculator IV method, the input expression is tokenized using the tokenize function. Then, the evaluation mapping for variables is created by combining evalvers and evalents into a dictionary. The tokens are evaluated using the evaluate function, resulting in a polynomial. The variable mappings are applied through the substitute method to replace variables with their corresponding values. Finally, the resulting polynomial is converted to a sorted list of terms using to_list, which is returned as the output. Here, we begin by defining the basic calculator IV method, which takes three parameters: the mathematical expression as a string, an array of evaluation variables, and their corresponding integer values. We first create a map called evalMap to store these variable to integer mappings. Then, we tokenize the input expression using the tokenize method, evaluate the tokens to construct a polynomial using the evaluate method, and finally substitute the evaluation variables with their respective values. The result, which is a simplified polynomial, is converted to a list of strings using the toList method and returned. The tokenize method processes the expression by iterating through its characters and splitting it into meaningful tokens. For example, operators like plus, dash, and asterisk are added directly, while alphanumeric sequences are grouped together as variables or numbers. In the continuation of the tokenize method, we handle the case where a sequence of letters, digits, or underscores is encountered. This ensures that variable names or numbers are correctly identified as single tokens. Once a token is constructed, it is added to the list, and the loop continues until the entire expression is processed. The evaluate method begins by initializing two stacks, one for polynomials and another for operators. Precedence rules for operators such as plus, dash, and asterisk are defined in a map to ensure correct handling of operator priority. We then iterate through each token, pushing operands like variables or numbers onto the polynomial stack. For operators, we handle parentheses explicitly, pushing opening parentheses onto the operator stack and processing until we encounter a matching closing parenthesis. When a closing parenthesis is encountered, we repeatedly apply operators from the operator stack to the polynomials in the polynomial stack until an opening parenthesis is found. For other operators like plus, dash, or asterisk, we apply the operator from the stack if it has higher or equal precedence compared to the current operator. This ensures the correct order of operations is maintained. Finally, after processing all tokens, any remaining operators are applied to the polynomials on the stack. The result of this evaluation is the top polynomial on the stack, which is then returned. The apply operator method simplifies the process of applying an operator by popping two polynomials from the stack, performing the operation based on the operator, and pushing the resulting polynomial back onto the stack. This structure allows us to modularly handle each operation type. In the apply operator method, we handle addition, subtraction, and multiplication operations. For addition, we combine the terms of both polynomials into a new result polynomial. For subtraction, we negate the terms of the second polynomial before combining them with the first. Multiplication involves pairing every term of the first polynomial with every term of the second polynomial. The polynomial class is introduced here to encapsulate the representation of polynomials. Each polynomial is represented as a map where the keys are lists of variable names and the values are their corresponding coefficients. The constructor allows for initializing a polynomial either empty or with a single term, depending on the input token. For numeric tokens, the polynomial is represented with an empty variable list and the coefficient as the token value. For variable tokens, the variable name becomes the key, and its coefficient is set to 1. The add method combines the terms of two polynomials into a single result. If a key exists in both polynomials, their coefficients are summed. The subtract method works similarly to the add method, but it subtracts the coefficients of terms in the second polynomial from the corresponding terms in the first. For terms unique to one of the polynomials, the coefficient remains unchanged in the result. The multiply method is slightly more involved, as it computes the product of every term in the first polynomial with every term in the second. The variables from both terms are combined into a new term, which is then sorted to maintain a consistent order. The coefficients are multiplied, and the resulting term is added to the result polynomial. This approach ensures that all terms are correctly combined and no duplicates are introduced. The substitute method replaces variables in the polynomial with their values from the provided eval map. For each term, we check if the variable exists in the map. If it does, the coefficient of the term is multiplied by the variable's value, effectively substituting it. If the variable is not in the map, it remains in the term. This ensures that only the provided evaluation variables are substituted while retaining any others. The toList method converts the polynomial into a list of strings. To ensure the output is in a standardized format, the terms are sorted first by the number of variables in descending order and then lexicographically. This guarantees that terms are consistently ordered, which is important for comparing results or debugging. The sorting logic is implemented using a comparator that prioritizes the variable list size. The toList method continues by iterating through the sorted terms and formatting each one as a string. For terms with non-zero coefficients, the coefficient is appended to the string, followed by the variables, each prefixed with an asterisk. This format ensures that the output is both human-readable and machine-parsable. Finally, the list of formatted strings is returned, representing the simplified polynomial. This marks the end of the implementation, where we've broken down the input expression, evaluated it using stacks for operators and operands, substituted variables with their values, and formatted the result into a standardized output. With this approach, the program can handle complex expressions involving addition, subtraction, multiplication, and variable substitution efficiently. To start, let's consider a simple arithmetic expression, 3 plus 2 * 2. The first step is tokenization, where we break down the expression into individual components, 3 plus 2 * 2. Next, we evaluate the expression. We follow operator precedence, where multiplication has higher precedence than addition. The first token 3 is converted into a polynomial with a constant value of 3, represented as polynomial terms equals 3. The plus operator is stored in the operator stack. Then, 2 is processed as a polynomial with a constant value of 2. The multiplication operator asterisk is added to the stack after checking precedence. The next 2 is also converted into a polynomial. Now, the multiplication operation is resolved first, yielding 2 asterisk 2 equals 4, which gives us polynomial terms equals 4. Finally, the addition is resolved, resulting in 3 plus 4 equals 7, represented as polynomial terms equals 7. Since no variables are provided in this example, the substitution step is skipped. The final polynomial, which represents the result of our arithmetic operations, is then converted into a list format. This gives us the output, 7. Now, let's move on to a more complex example that includes variables. Consider the expression a asterisk b plus 2 asterisk a with a set to 3. Tokenization breaks this expression into a asterisk b plus 2 asterisk a. This prepares us to evaluate the expression step by step. In the evaluation step, we begin by processing the tokens while respecting operator precedence. The first token, a, is converted into a polynomial terms equals a comma 1. The multiplication operator asterisk is stored in the operator stack, and the next token, b, is processed as a polynomial terms equals b comma 1. Multiplication is resolved first, resulting in a asterisk b equals polynomial terms equals a b1. The next operator, plus, is added to the stack. Then, the constant 2 is processed as polynomial terms equals 2, and the multiplication operator asterisk is stored. Finally, the token a is converted into polynomial terms equals a comma 1. The multiplication operation resolves to 2 asterisk a equals polynomial terms equals a comma 2. Now, addition combines the results, yielding a asterisk b plus 2 asterisk a equals polynomial terms equals a b1 a comma 2. After evaluation, we proceed to substitution. In the substitution step, the variable a is replaced with the value 3. This updates the terms as follows: a b becomes 3 asterisk b with a coefficient of 3, and a comma becomes 3 with a coefficient of 6. The resulting polynomial is polynomial terms equals b comma 3, 6. For the output conversion, the polynomial is transformed into a list format, resulting in 3 asterisk b, 6. This gives us the final output for the expression with variables. Now, let's explore an example involving nested parentheses. In this example, the input expression is a plus b asterisk 8b. Tokenization breaks it down into a plus b asterisk a dash b. The parentheses are processed first. The inner expression a plus b is evaluated as polynomial terms equals a comma 1 b comma 1, while 8b evaluates to polynomial terms equals a comma 1 b comma minus 1. These results are then multiplied together. The expansion of a plus b asterisk 8b gives a asterisk b plus b asterisk asterisk b. After simplifying, the terms become polynomial terms equals a 1 a b0 b minus 1. Since no variables are provided for substitution, this step is skipped. Finally, the polynomial is converted to a list format, yielding asterisk a b asterisk b. This is the final output for this nested expression. When analyzing the time complexity of our solution, the first step is to consider the process of tokenization. Tokenization involves scanning through the input string character by character to break it down into tokens, such as variables, numbers, or operators. This operation is linear with respect to the length of the expression, so it takes n time. Next, we have the parsing and evaluation phase. Here, we use a stack-based approach to manage operators and operands, including handling parentheses. Each token is either pushed onto the stack or evaluated immediately, which also operates in n time since we process each token once. However, the complexity increases significantly during multiplication. When multiplying two polynomials, each term in one polynomial has to interact with every term in the other. If the two intermediate polynomials have m1 and m2 terms respectively, this operation takes m1 asterisk m2 time. As we repeatedly evaluate and multiply larger polynomials, the worst-case complexity becomes k squared, where k represents the maximum number of unique terms in the resulting polynomial. Now, let's consider the substitution and sorting steps. Substitution involves replacing variables in the polynomial with their corresponding values from the mapping. This requires iterating through all terms in the polynomial, so if there are k terms, substitution takes k time. Sorting is the next major step, where we arrange the terms of the polynomial by their degree and lexicographic order. Sorting k terms has a complexity of k log k. Overall, the time complexity of the solution is dominated by the evaluation and multiplication steps, leading to a worst-case time complexity of k squared. Here, n is the length of the expression, and k is the maximum number of unique terms in the polynomial. These steps ensure that even for complex expressions, the operations are handled efficiently compared to a more naive approach. For space complexity, the first factor to consider is the storage required for tokens. Tokenizing the input expression involves creating a list of tokens, which requires n space, where n is the length of the expression. Next, intermediate polynomials generated during the evaluation step demand space proportional to the number of unique terms. If k is the maximum number of unique terms, the space required for storing all intermediate polynomials is k. Additionally, the parsing process uses two stacks, one for operators and one for operands. The size of these stacks depends on the depth of nested parentheses and the total number of tokens, which is at most n. Finally, both substitution and sorting operate on the polynomial representation, requiring k space for terms and an additional k log k for sorting. These factors contribute to the overall space requirements of the algorithm. Bringing all these factors together, the overall space complexity of the solution is n plus k, where n is the length of the input expression and k is the maximum number of unique terms in the polynomial. To put this into perspective, let's compare it with a brute force approach. A naive solution would involve expanding all possible products and explicitly storing every term, resulting in an exponential blowup of 2 to the power of n in the number of terms for large expressions. In contrast, our structured polynomial operations avoid this by efficiently combining like terms and using hash maps. This reduces the worst-case complexity to n k squared, 4 times n plus k, for space. Moreover, the optimized use of hash maps and sorting ensures that redundant terms are not stored, making the solution significantly more efficient than the brute force alternative. Finally, let's summarize the best, average, and worst-case scenarios. In the best case, the expression consists only of constants or a minimal number of variables, with no nesting or multiplication. Here, the complexity simplifies to n for tokenization, parsing, and evaluation. In the average case, we deal with moderately sized expressions that include some nesting and a smaller number of unique terms. This results in a complexity of n k squared. The worst-case scenario occurs with deeply nested expressions that involve extensive multiplications and a large number of unique terms, where the complexity remains n k squared. Overall, the implemented solution strikes a balance between efficiency and correctness, providing manageable complexity without resorting to a brute force approach. This makes it well-suited for handling even intricate mathematical expressions. When tackling this problem, it's easy to fall into the trap of overcomplicating your solution. Many candidates try to optimize their code prematurely, before fully understanding the problem requirements. This often results in convoluted code that becomes hard to debug. Instead, focus on starting with a simple brute force approach to ensure correctness, and then optimize step by step. Another common mistake is ignoring edge cases. Scenarios like empty inputs, single-element inputs, or boundary conditions such as maximum or minimum values are crucial to consider. Overlooking these can cause runtime errors or incorrect results. Additionally, when dealing with nested structures, such as recursive calls or multiple loops, it's vital to carefully manage indices, recursion depth, and stack space. Mismanagement here can lead to logical bugs or even stack overflow errors. Lastly, time complexity analysis is frequently underestimated. For instance, misjudging an algorithm as n log n, when it's actually n squared, can cause your solution to fail on larger test cases. Always evaluate the complexity of your approach thoroughly. Another pitfall is not validating inputs properly. Assuming that inputs are always valid can lead to undefined behavior. Always take the time to check for constraints like null values, invalid formats, or numbers that fall out of the acceptable range. Now, let's talk about interview dynamics. Clear communication is essential. Walk your interviewer through your thought process, explain why you're considering a particular approach and how it addresses the problem requirements. Being able to identify common problem patterns, such as sliding windows, dynamic programming, or divide and conquer, can be a huge time saver. Additionally, be ready to discuss the trade-offs of your chosen approach. Are you prioritizing time complexity, space efficiency, or code readability? It's also important to optimize iteratively. Start with a straightforward solution to establish correctness, and then refine it step by step. Finally, practice debugging as part of your preparation. Simulating the process of stepping through your code with sample inputs can help you catch errors before running it, which is a valuable skill to demonstrate during an interview. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 20 valid parentheses focuses on working with stacks and nested structures, which is a foundational concept for this type of problem. Another excellent example is LeetCode 394 decode string, which involves recursive parsing of nested expressions. If you're looking for more experience with mathematical expression parsing, LeetCode 227 Basic Calculator 2 offers a great opportunity to practice. Lastly, LeetCode 241 Different Ways to Add Parentheses applies a divide and conquer approach to evaluate all possible outcomes of an expression. These problems not only build your problem-solving skills but also help you recognize patterns that can be applied across a variety of scenarios. There are also alternative approaches to consider for problems like this. The divide and conquer method, for example, breaks the problem into smaller subproblems and solves them recursively. This approach can be intuitive for parsing expressions, but it may require additional space due to recursion. Dynamic programming is another option, particularly useful when the problem involves overlapping subproblems. However, the trade-off here is that it often demands significant space for memoization tables. An iterative solution with stacks is a popular alternative, as it is generally more space-efficient than recursion. On the downside, it can be less intuitive to implement, especially for deeply nested structures. Finally, greedy algorithms can sometimes simplify problems by making locally optimal choices at each step. That said, they may fail in scenarios that require a more global optimization strategy. Understanding these approaches and their trade-offs can help you choose the best solution for the problem at hand. Great work! To recap, we delved into the basic calculator fork problem, discussed its challenges, and outlined the brute force approach. We also highlighted the importance of parsing and recursive techniques. Keep practicing, and don't hesitate to refine your skills further. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!